All right, so let's go ahead and talk about linear functions here. There's a lot going on algebraically with this, and we should have some familiarity with linear functions based on what we learned in Algebra 1. One of the main things that came out of linear functions is that we should know that we should have a constant rate of change for any linear function. Now, you might have also seen it referenced in a couple different other ways. We've certainly heard of the word slope. It's a little bit more, I'm going to say, geometric based, or when we have images involved. We also know we've talked about the change in y over the change in x. So these are all different ways that we express that constant rate of change. For us, in this situation here, for these notes, let's go ahead and take a look at the problem we had at the beginning, and we should see the phrase stick out, steady rate. So that's the drip here for this IV machine. So that phrasing steady rate, that's our constant rate of change in this situation. So we understand that this table should provide to us a situation where we have a constant rate of change and it is in fact linear. But let's go ahead and just take a look in terms of how that plays out with our numbers here in the table. So I'm going to be able to take any pair of the four numbers I have in this table. I'm just, for purposes of examples, let's go ahead and take a look at 1365 and 1295. So our 2 points in this scenario, we can see as we have 1365 and then we go to 1295, that would involve a drop of 70. And as we take a look at the corresponding x values, or the corresponding inputs for those outputs, we go from 10 to 30. Well, from 10 to 30 would be an increase of 20, right? We take 10, we would add 20 onto it to get to 30. So just for the purposes of argument here, I'm going to store up that rate of change. That rate of change was negative 70 over 20. Again, our output changing down, going down 70, our input going up 20 in that same situation. I'm going to, just for argument's sake, take a look at the last 2 points in this table. And again, the concept here, let's go ahead and take a look at our outputs, or our y values. I have 1120. I'm going to go ahead and subtract 595 from that. And that would be us having a decrease of 525. And if I go take a look at the corresponding inputs again, I'm going from 80 to 230. 80 to 230 is definitely a larger jump from 0.3 to 0.4 on the x values compared to 0.1 to 0.2. And I get 150. Now, wait a minute. This should be a constant rate of change. And when I did that from 0.1 to 0.2, it was negative 70 over 20. Here, from 0.3 to 0.4, it's negative 525 over 150. Well, we can definitely go ahead and actually figure out what is that legitimate rate of change. And if I did 720 divided by, 70 divided by 20, that is negative 3.5. And there's a bunch of ways you could write that. Technically, it's also negative 3 1/2. Maybe you would think about it negative 7 over 2, so on and so forth. Interestingly enough, and you might have already anticipated this happening, but if I did negative 525 divided by 150, I have the same exact decimal value play out. It's negative 3.5 each time. So what we're saying here is that our rate of change, our slope in this scenario, is actually negative 3.5, and that would be constant throughout all of this table. I could do 0.1 and 0.4. It would be still negative 3.5. 0.2 and 0.3, I could do that. And at the end of the day, when I typed it into a calculator, if I reduce the fraction, I'm getting negative 3.5 as my rate of change. It's constant because it's linear.